Okay. Uh, so every morphism F in our category C has a factorization of type, uh, say, F. Mhm. Uh, G that is in that is a relative cell complex inclusion. Uh, and say Q that has right lifting property against all morphisms in I. So this is a small argument.
Okay. Does everyone remember what cell of I means? Okay. If there are things which don't make sense or which you have forgotten, please do not hesitate to ask Mikhail.
Okay. Proof. Call S1 is a set of all lifting problems between F and morphisms from I, as it is a set of commutative diagrams of this type. I from I. Yeah. It left is at 0. The X. So you can define Z1 as the child of the diagram it looks like that. So we take all all the diagrams of commutative diagrams of this type, and taking co-product of all arrows from the left and attaching them all to Z0. So we we get a big object that is X with attached many attached cells. And we want a morphism from Z1 to Y. Now, so we will get it from universal property of washout. We have morphism from X to Y, that is just F. And morphism from coproduct of all of J. It is a coproduct of all these arrows from these creative squares. And so we have a universal arrow that we call Q1. The next step is to iterate this process. So we can define that alpha for every ordinal alpha, and how we get that alpha plus 1, we doing the same process. We look at the set of all lifting problems. And doing the same. And it's important we have a morphism from all that alpha to Y. Morphisms here alpha that that is that gives us a factorization of F, and everything commutes. Yeah, we can call this inclusion A alpha. So we have a factorization of this type. We will stop our iterating. If we have a limit ordinal, we just take a co-limit of all previous z betas. Yeah, and a alphas is in cell R by construction. We just attached the cells from R. Okay, but in the statement of our theorem, we want for Q to be to have a right-listing property against all i's. So why is that? We will stop our process at a sufficiently large ordinal beta such that all that would be kappa all domains of arrows in I is kappa small. So the domains is this big case. Okay, so we want to show that for every diagram, for every commutative square, of this type, we have lifting. Why is that? The map K the map yeah, the map this diagonal map factors through some z alpha because K is kappa small and sorry not this one but this one arrow factors through some z alpha because the K is kappa small and that K is a co-limit of an kappa filtered diagram just because it is a transferring composition. Series. So we have a diagram of the type. Well, that will be K kappa. This is K. Okay. So we have a map from L to Z alpha plus 1. because the top plus one is a hash out of some diagram. And this diagram is an element of an index set in here. No, as well. So we have this is L. We have it here, just as an one element of this coproduct. So we have this map. So we have this diagram. It is K alpha is I. It's called inclusion of L. And all this since well, I have so that that's right. So we have map for Y. Everything we use. So we just had we just constructed the lifting map from L to Z kappa that we wanted. Maybe in this diagram we hardly can see that it is a lifting. So we put more. And to add, we have factorization of the type we want.
Okay, well, I'll just add that this is a very important theorem, and it's due to Quillen, and it's one of the main ingredients why model structures actually work. It's well, it's something like low-level level manipulations with memory when it comes to computer programming. It's normally hidden inside a black box, and people don't see it, but nevertheless, it's necessary for a computer to work. Well, today we've had a glimpse of this black box.
Okay. Definition. A model category C is cofibrantly generated if there are small sets I and j such that of I is a class of cofibrations of C. Maybe I recall that of I is a class of retracts of cell inclusions, cell attachments, morphisms in I. Cof of J is a class of cyclic cofibrations. In C. And I and J admit small object argument. Which means that all domains of morphisms in I and J are kappa small and kappa. So this is a definition. Proposition in a cofibrantly generated model category. We have that class of cofibrations in C is LLP of RLP of I, and the same is for J. So this is a way to construct this is a way to construct the cofibrations in C, this cofibrantly generated from a small set of morphisms just by taking all morphisms that have right lifting property against morphisms in I, and and then taking the morphisms that have left lifting property against those morphisms. So it is a good factorization of configurations. Why the proof of the proposition? This argument is the same for I and for j, so we will take I. It's clear that I contains in LP of I. And we already know that the collection of morphisms that have LLP against something is closed undertaking washouts, transfinite compositions, and retracts, and co-products. So we know that from here that is that cof of I is contained in this class. So have to prove the converse inclusion. We will use the small object argument. Left f from x to z. C be in this class LP of I. So we can factorize it into the composition of cell I, or a morphism from cell I. Say f prime. But I will write not this, not cell I, but conv I. It's this. I can do this because cell I contained in conv I. And f prime that has RLP against I. And we can use a retract argument that we already used last time. To show that f is in of I. So we have the diagram of this time. F is factorized the composition. And we know that F has left lifting property against all morphisms that have right lifting property, and we know that F prime prime is in LP. So we can we have a listing, say secret. And then we have a retract diagram. So F prime is a retract of F. Here we have here we have F prime. So F prime is a retract of F. No, so vice versa. F is a retract of prime. So and F prime is in conf I. So the F is in conf I. And we proved the converse inclusion here. And we're done. Let's recall when we started to talk about having the generated categories, model categories, because we wanted to find the properties that gives us existence of factorizations from the theorem we proved last time. Call that the ones that the factorizations of the type cofibration that is followed by cyclic vibration and anytime map that is followed by vibration. So proposition, suppose that C is coherently generated model category. Recall that the C is a category that we're transferring as a model structure to the D. Suppose that C is coherently generated. And F preserves small objects. F is left adjoint functor. And use right adjoint. Which means that if X is small, kappa small. So the F of X is kappa small. Then everomorphism in D factors are like this. And moreover, if model structure, if right transverse model structure in D exists, transferred or model structure on D exists, then D is itself coherently generated. And for a set of generators, we can take f of I and f of j. If I and j is generators in C.
Well, I've forgotten what exactly is I and what is J. I is the class of generating covibrations, and J is the class of generating acyclic covibrations.
Yes.
Okay.
Both. By is small object argument. We have wait. Let's be okay. Okay. I want to say that in the definition of right transfer to model structure, we defined vibrations and weak equivalences as morphisms that which images are vibrations or weak equivalences, respectively by bisection of functor U. So F vibration weak equivalence if and only if U of F is so in C.
it's better to say such.
Such.
And please recall that U is a right adjoint, and there is a left adjoint, which is F.
No. I want to say that equivalently, we can say that the vibrations is the map that have right lifting property against images of configurations in C by the functor F. So we have configurations in C here. We can take images of these configurations by I. And so the vibrations is or maybe I will talk about vibrations. If a map has right lifting property against these maps, that is not configurations in D, but some maps. So if F has RLP against these maps, then it is a vibration in D in our first definition. Why is that? It is because because we have jointness. So if we have the diagram of this type, and want to know if this map, this right map is a vibration. By jointness, we have a diagram of this form in D. This is diagram in C. This is diagram in D. And we want to know if this is a vibration. So we have a lift here. If we don't lift, we have lift here. So this is precisely what we stated. This is a configuration. And this is the image of configuration. Well, I said something wrong. A cyclic configuration. And analogously, the F is an acyclic vibration if it has an RLP against images of all co-vibrations in C. So we can write vibrations in D. LP of f of I, f of j. So, and cyclic configuration CV is in LP instead of I. Yes. Okay. So by the small object argument, we have for every map a decomposition of the type. Um, so I so f of I small object argument that we use for f of I which we which was I in the statement of the theorem will be f of I now. And RP. So we can write of I here again because the cell of f of I is contained in cof of f of I, and by this proposition, this one, we know that cof of I is a LP of I f of I. So we have a decomposition in the factorization in the morphisms from such classes. So how we said earlier, this is vibrations, and this is a morphism that have left lifting property against all vibrations. This is an anodyne map by definition. So we have a decomposition, a factorization in the composition of anodyne map that is followed by a vibration. The first one, second one. And the first one, analogously, but we will write f of j here, and f of j here. So it will be LLP against all cyclic vibrations. And this will be co-vibrations by definition of co-vibrations in category B. So we have the factorizations that we want. Okay. So in conclusion, we know that if category C is covalently generated, and the left adjoint functor preserves small objects, then we have a part of our theorem, the first condition in our theorem that in our characterization of in our criteria of existence of right transfer structure. Yes. So now we will talk about the second condition, that is anodyne maps are with equivalence. If there is no questions by now.
Well, this property that anodyne maps are weak equivalences is also called acyclicity.
Yeah. Okay. Proposition. Again, we are in situation of homogeneous functors F and U. So these are at adjoint. Suppose that first D has a fiber replacement functor.
Or just fibrant replacements.
Or just fiber replacement that is no that is not functorial. Not necessarily functorial. That is, if we have enough.
Значит, Миша, на всякий случай сохраните, пожалуйста, записки, а то, значит, заряда осталось немного, и все может пропасть.
Да, Никита, сохранить записки прямо сейчас. Прямо сейчас сохранить записки. Все сохранено. Okay. If we have a morphism from X to Y, packet placement, let's call it R. So we have the diagram. This type RF. This is work equivalences. And RF and Rx and Ry are fibrant objects. And RF is a fibration. In the second one, suppose that D has path objects. All hybrid objects. Which means that if A is 5, right, we have a factorization of the diagonal map. From A to A cross I, as a weak equivalence, followed by equilibration. So then anodyne, any anodyne map in D is weak equivalence. Okay. The proof. Let's draw a big diagram. Yeah, let's call this inclusions. This maps from X to Rx, that is weak equivalences. JX and JY. So what's going on here? Here we have two squares that are pullbacks. So the first one square, this one, is a pullback of RF by the projection of cross product by the first, sorry, I have one here, to the first RY. And the second one is pullback of the pullback of RF by this map that is a component of factorization from the second condition. That is, here we have P of Ry and have a factorization of a diagonal map in the composition of weak occurrences and vibrations. So we want this square to be a callback.
Pullback.
And we want now a morphism from X to this object. PRF is just обозначение, notion. Notation. It's just a notation for this pullback. So it's not a subject of RF. Okay, why we have morphism from X to PRF? Because we have a commutative diagram. One can check that all commutes. Maybe we will not stop here. Okay, then we have something like that. Okay. Let's see. Well, this diagram is commutes because the upper one commutes. F composed with JY commutes because this one is identity, because it is a diagonal map that's followed by projection. So this map from this X to this Ry is just a composition of F and JY. It's the it is this triangle, and for this triangle we will just take Y I and the projection to R1. So everything commutes. And this P will play his role later. So we want to prove that if this F is anodyne, then there's a weak occurrence. let's see. The morphism. F is anodyne, so it has a lifting property against all vibrations. So we want to prove that this map, that is just a projection of PRF to R1, is a vibration. Why is that? Well, I state that let's look here. Projection of PRY to RY. Why this is a vibration? Well, because this map is a vibration and this projection is also a vibration, because RY is finite object. So the composition of two vibrations is a vibration, and pullback of vibration, that is a projection of PRF to Rx, is also a vibration. RF is a vibration by the definition of vibrant replacement, so the projection is a vibration. So this is a vibration. And we have a lift. We get a lift. Let's go check. Now we want to prove that I is a weak equivalence. Let's return here to the projection of PRY to RY. I state that it is not only a vibration, but it's an acyclic vibration. Why? Because this map from the upper one RY is an identity that is weak equivalence. And this map is weak equivalence by the definition of Kasach. So by total three property, this projection is also weak equivalence. Moreover, it's an acyclic vibration, so the pullback of an acyclic vibration is also acyclic vibration. So P.
No, why is acyclicity preserved? The pullback of a vibration is a vibration. Okay, but why is acyclicity preserved in this case?
Yeah, pullback of a weak equivalence is not necessarily a weak equivalence, but a pullback of an acyclic vibration as a one one word, one sentence, pullback of an acyclic vibration is an acyclic vibration because a class of acyclic vibrations is exactly a class of maps that has right lifting property against all co-vibrations, and this class is stable under taking pullbacks. So we know that F.
Okay, does everyone agree with this argument?
Okay. Okay, we know that P is a weak equivalence. And we know that P composed with I is JX. That is also weak equivalence. So by the thought of three property again, I is a weak equivalence. Also, we know that JY is a weak equivalence. So let's take a look what we get. X, Y, ERN, and RY have J, G, this projection, and here we have I, and here we have J. So we know that I is a weak equivalence and JY is a weak equivalence. 2 out of 6 properties says us that if we have 4 objects and morphisms like that, such that the composition of the first 2 is a weak equivalence, and composition of second 2 is also weak equivalence. If I and JY are weak equivalence. So are all morphisms here. So are F, J, and okay, let's call it eta. So
why is this true?
This is true because the 2 out of 6 property is true for isomorphisms in every category, not necessarily a model or categories. It is an exercise for the listeners. Exercise on category theory. And we know that if we have a model category, we have puncture to its homotopy category. That is also a localization of category C in weak equivalences that takes weak equivalences to the isomorphisms. So if we look at this diagram in the localized category, then we can use 2 out of 6 property to the
why the localization functor takes weak equivalences to isomorphisms, but why is the converse true?
We talked about it the last time. Alexei said something about that. That the map F is a weak equivalence in C if and only if it has F has homotopy inverse. So if and only if this map.
Yes, but this is true for a map from a cofibrillant object.
Okay.
Well, in this form, I think we need both objects to be both fibrant and cofibrant.
Okay. We know that homomorphisms in the homotopy category of C between every two objects, not necessarily cofibrant or fibrant, non-fibrant, is class of homomorphisms in C between cofibrant and fibrant replacements. Think lengths factored by the homotopy relation. So if we have a map that is a weak equivalence, yeah, we have a map. Yeah, let's write. Maybe let's write something different. Look. So Ivan Spinensky. Yeah. Let's write something like that. Alexei also said that if we have let's say fibrant replacement of weak equivalence, it is also weak equivalence if I'm not trying to mystify. Yeah, okay, let's say it's true. Then if we have a map F, so we have its fibrant replacements RF. The same is true for cofibrant replacement. So we have F, we have QF, we have RQF. All those maps are weak equivalences. And for RQF, we can use this theorem. So F, this RQF has a multiple inverse if and only if F is a weak equivalence. But in localized category, the objects, the morphisms between X and Y and morphisms between RQX and RQY are the same. So if F was an isomorphism here, then it is if F was an isomorphism here, in homotopy category, if F was an isomorphism here, then it is an isomorphism here. So I think this statement.
What we get is only weak equivalences go to isomorphisms.
Yeah.
Okay. We I think we've been Mikhail has been talking for an hour and a half, even more. Do we need a break?
I think I need only 15 minutes to finish my talk.
Which in practice sounds like half an hour.
Окей, мне осталось сказать только, ну, по сути, вот я договорил про теорему, мне осталось сказать, что
Хотелось бы еще применить
Да.
вот эту теорему к интересующему нас случаю, значит, СДЖ.
Да, и мне вот осталось только про это сказать, это не займет много времени.
Ну, хорошо, я...
Потому что я не буду ничего доказывать. Просто
нет, там все равно, то есть уже большая часть доказана, там все равно хотелось бы что-то проверить. Ну, давайте сделаем там перерыв 15 минут и, значит, потом продолжим.
Okay.
So let's have a break for quarter an hour, and then Nika will finish the talk. And now we want to apply what we've seen so far to the forgetful functor from CDJs to co-chain complexes, which we may assume positively or non-negatively graded.
Yes. Right. Have a great functor and the forgetful functor, and it will be graded. CDJs and chain complexes. So we want to check the conditions from our two propositions. Firstly, we should check that the category of chain complexes is cofibrantly generated. And
Well, let's assume it is.
Okay, maybe I can just
But let's write the generating.
let's write the
let's write the classes I and J.
Yeah. A class I that is generator of cofibrations looks like that. By Q of n, I mean that a complex that is at a zero everywhere but in n's place. And homology of this complex is just Q in n in n's tens plus and Q n minus 1 n is a complex that also zero everywhere, but it has two Q's on n's and n minus 1 places. And here is an isomorphism. Here is an isomorphism. So
Well,
this complex,
since we deal with co-chain complexes, probably n minus 1 should come before n.
okay. So this complex has no homology. And J is this one. So as this complex has no homology, this inclusion is we could call this quasi-isomorphism. So yeah, this is this the sets of generators. Yeah, one can check that the classes of cofibrations is and acyclic cofibrations are RLP of LLP of RLP of this one. So we second we should check that functor f preserves small objects. We need to say something about small objects in categories of chain complexes and CDJs. Well, I state that statement if chain complex is finitely generated as a vector space. Then it is small and small. Why is that? Because
well, this is sort of straightforward.
yeah, if we have the diagram, unfiltered diagram, and the co-limit, let me say check. And the co-limit J to complexes. So how can we chain complex and we have morphism from M to co-limit of F. How can we build a lifting? We just can lift the images of the generators. Have lift at some floor of this diagram for every generator, and the highest floor we lifted all the generators, so we lifted morphism from M to coding. Another statement we can say about the CDJs. If CDJ is finitely generated as an algebra, then it is small. The proof is the same. So our functor f is a free functor. A free functor applied to a finitely generated chain complex is finitely generated as an algebra with the same set of generators. So if object was finitely generated, then its image by applying a functor f is small. In our case, we have only finitely generated chain complexes, so we add that here. So we didn't prove that f preserves all small objects, but we proved something sufficient for parse.
Well, for general kappa, the strategy is more or less the same.
Yeah. Okay. Well, I mean, I didn't prove that if object is small and small, then it is finitely generated in some sense. So we don't need it. Oh, okay. Next, we want to check the conditions from the second proposition, which is that D has a finite replacement. D has a finite replacement, and D has best objects. This this is this is true because we have surjective trick, which we talked about.
Well, firstly, for fibrant replacements, we needn't do anything. All objects are fibrant.
Well, all objects are fibrant, but for our proof of the proposition, we use the fact that RF is fibration. So we should.
What are fibrations?
Fibrations are in the category of CBJs. The fibrations are component-based surjections.
Yes. So the fibrations are very simple.
Yeah.
They're just degree-wise surjective maps. And so the only thing we need to check is the existence of path objects, which is basically the surjective trick we saw in class.
Yeah. So for existence of path objects, we use the surjective trick for all F morphisms F from A to B. We have a factorization for the type. Yeah. So for a morphism from from a diagonal morphism, it gives us exactly a space object. Okay. And yeah. So we check. I have checked everything that we wanted, I think.
Okay, so Misha, please save the notes and send them to me, please, by email after the talk, after we're done.
Okay.
Are there any questions to the speaker?
Yes. Can you please send the notes and the article to our chat, please? Or I don't
yeah.
know, email.
Yeah, I can send a link on the NCAT page.
Oh, okay.
And maybe this file will send Alexei Gennadievich to all the participants, of course.
Okay, thank you.
Any more questions? Okay, then let's stop the recording